now you're all looking at my whiteboard, basically my desktop. And we're going to start off with an introduction, give you an idea of what is Calc 4 about, you know, if you want to put it into perspective. Well, Calc 4 really does or deals with the calculus of multidimensional functions. So we just take basically Calc 1 and Calc 2 and a little bit of Calc 3, but not really so much. And we just take them to the next step. What do I mean by that? Well, if I said to you y equals f of x, and I said to you, we are going to differentiate it, we might use that notation. We might use that notation, right? But you know what we're talking about, right? Differentiate. Right? It allows us to find out things like the slope of the curve at a point. But you can also use derivatives, can't you, to do things like rate of change. You can also use derivatives to find local max, right? The tops of hills or the bottoms of valleys and so on and so forth. And that's basically what Calc 1 does, isn't it? How do you differentiate things and what can you do with those derivatives now that you've found them? Now, if I asked you to find that guy, you would all say, oh, you want me to integrate the function. That's the typical notation that we use for integrals. And that's really what Calc 2 is about. Isn't Calc 2 how to integrate functions and what can you do with those integrals? And you can do all sorts of cool things with integrals, from finding the area under a curve, but can't you also use integrals to find volumes of revolution, surface areas, distance traveled, all sorts of cool stuff, right? So Calc 2 is how do you find integrals and what can you do with it? Calc 3 doesn't fit very nice into a one box deal. Calc 3 is a kind of where you put all the cool stuff, but you didn't really know where else to put it. So it does things like sequences and series, which we won't do anything with in Calc 4. It does some stuff with vectors, which we will do when we do vector functions. And right at the end, you did a thing called partial derivatives. Remember those guys?
I do.
Well, that's where Calc 4 is going to be. The difference with Calc 4 is that we don't have a function of one variable, you know, like x cubed plus x. We have a function of two or more variables. And z could be, for instance, x squared plus y squared. And that's an example of a multi-dimensional or multivariable function. So for any given x and y, isn't there going to be a corresponding z? So you might think, well, how can I visualize that? I know how you visualize y equals f of x. I mean, our calculator can do that, right? Isn't it just a curve in 2D? So if you plotted all the points that had the relationship that the y coordinate was, say, x cubed plus x, it might look something like that. So how do you do these guys? Well, the first thing is that this is not a line. This isn't a line, actually it's a surface. And that means we have to figure out some way in which we can visualize what this multidimensional, multivariable function looks like. And here we have a problem. It's a major conceptual problem. And the problem is that we draw on two-dimensional paper for something that is a three-dimensional surface. And so we have to try and figure a best way that we can simulate 3 dimensions in 2. Now, what you've noticed I've drawn here is the x, y, and z axis, and right in the center is the origin. And the first thing that strikes me is that the orientation of the x-axis is coming out of the paper towards you, which is really weird. And then the y-axis values go like this. And the z-axis values go like this. And I can't remember, I think it's called the right hand or the left hand rule. So the reason we need this weird orientation is to do with 3 fingers going like this or 3 fingers going like that. I think it's a left hand rule. And if you orientate them, this finger has to be X, this has to be Y, and that has to be Z. And the reason they need that is to keep the physics people happy, because they want positive to be up, meaning Z has to be up. And so that's the orientation that we're stuck with. So we are going to take functions like this and we're going to differentiate them. But when we differentiate them, they're going to be called partial derivatives. That's the bit you caught at the end of Calc 3, right? Partial derivatives. Okay. Or we're going to integrate them. And that's basically what Calc 4 is going to be about. How do you differentiate and integrate multi-dimensional functions? And what can you do with these derivatives and integrals once you've figured out the algebra of how to do it? You know, what can they be used for? Well, they can be used for all sorts of cool stuff. You can use them to find the volume of weird shapes. You can use them to find the centroid of a 3-dimensional object, right? The center of mass, if you want to call it that. You can use these things to find the mass of an object, the density of an object. You can use it to find the top of a hill in 3D space or the bottom of a valley. You can then move on to 4, 5, and 25 dimensions, in which case don't even try and imagine what they look like visually because your brain will work. But we can find derivatives and integrals for 20-dimensional functions if you really wanted to. We'll focus on just doing these guys, which are 3-dimensional. Why the 3-dimension? X, Y, Z, right? You need 3 dimensions to draw them. So what does this guy look like? Well, I'm going to draw a really bad version of him. Can you imagine an acorn or a cup or a monk's cap turned upside down, pointing upwards? The surface of that shape are all the points that have the relationship that if you square the x coordinate and you square the y coordinate and add them together, that gives you the z coordinates of that point. So can you imagine the point that was 2, 2, right? X was 2 and y was 2. Wouldn't the z be 8 at that point? Now, we wouldn't expect to, and nor would I ever want to, try and take this and figure out what those are by hand. So let me take this as a good point to stop and move you over to our Canvas site, where you will be able to see, hopefully, because I got it set up. Right. Are you looking at our Canvas site? Is that what you can see?
Yes.
Yeah.
Oh, cool. Right. So in this here, we have the intro stuff. So this is where you find out how to log on to WebAssign, which is where all your homework, all your tests, apart from the final, will be found. The fact that you're here probably helps the Zoom page thing, so I'm assuming that you figured out how to do that. And then if we scroll down here, yeah, let's pause, backtrack. Let's look at some stuff here. If you click on this, you will see the first 2 weeks, what we're going to cover. So it's going to be starting at, well, that's WebAssign, but you know, you can figure that out yourself. But starting at 14.3, partial derivatives, and finishing at 14.8. So in that chapter, we're going to learn how to do derivatives. They're called partial derivatives when you do multivariable functions. And we're going to look at how to find derivatives, how to use a technique called chain rule, how to find another kind of derivative called a directional derivative, how to use derivatives to find maximum and minimums of surfaces. Okay, imagine that a surface was like a 3D flowing English valleys and hills, you know, hills and valleys. Wouldn't it be nice if you could locate where the tops of the hills are? They're called the local maximums, and where the bottoms of the valleys would be, and they're called local minimums. Just like in the old 2D, right? Top of hill, bottom of valley kind of thing, right? And we're going to show you that you can use partial derivatives and a little bit of algebra to locate those places and to find out if they're local max or mins. And you'll find out there's some situations where they're neither. So after 2 weeks, you'll get a test, and the test will always be on Monday, and it will be in this class time, and it'll be 8 to 10. Now, if 8 to 10 doesn't work for you because you've got a class right after this one, tell me and I can shift the test a little bit to suit you, right? And test 1 will be on chapter 14. And then the next 2 weeks, we do 15.1 to 15.5, where we look at how to do integrals of multivariate functions. And they're called things like double integrals and triple integrals, but you know, they're integrals nonetheless. And then you do the next 2 weeks, you do the rest of double and triple integrals. And you'll use some of the techniques that you use from Calc 2, you know, like power rules, and I know that the integral of cosine is sine, you know, things like that. And you'll get introduced to some new things. Not as many new things as you think. You remember in Calc 2, you had to learn techniques like integration by parts and U subs and trig subs and a whole load of other kind of little tricks of the trade. And we don't have so many of those types of tricks of the trade. We only have one, and it's called a Jacobian. And a Jacobian is just a fancy version of a U sub of a multidimensional function. So you'll pretty much be doing normal kind of integration techniques without too many clever ones, most of the time. And then you get a test. And then the next 2 weeks, we start doing vector functions. And vector functions are totally new. And I won't say anything about that until we get to it, but they're really cool. So if you are going to do any kind of engineering, trust me, if you're doing any kind of constructional engineering, right, anything with physical things that move, you're going to use vector functions. You really are. So we're going to show you what those darn things are and how you can use them to calculate things. And the next 2 weeks does the same stuff, but we use specific, what are called theorems. So basically, some clever guy called Stokes found a shortcut way of doing a really hard question. And it's called Stokes' theorem or Green's theorem, depending, or divergence or curl, depending on the situation. And then we have a final. So you can see planned. I got your whole life planned for the next 11 weeks as far as Calc 4 is concerned. Any questions about that, or do you feel comfortable about you get the gist of it? Right, so we work on a 2-week scheme. Now that means homework is due midnight, Sunday the 17th. That does not mean you start your homework 11 p.m. on Sunday the 17th, because that won't work. If you want to be successful in this class and you don't want to lose all your hair, every time we do something in class, try and do the homework from that section so that you're just doing it as we go along, right? It's good practice. It gets you to figure out, do you really understand what I'm saying? Because you might say, oh, yeah, that makes sense, no biggie. You don't really know until you've tried some questions yourself. And then you go in and you go, maybe I need to do an office visit. And we have office hours at Zoom. It's actually directly after this class. every day. But if that time doesn't work for you, we can arrange other times and I can go over stuff for you. And of course, you can shoot me emails. Email and Calc 4 don't work well. First, it's very hard to write an email with the math that you're dealing with. Right? The email text is very messy. I mean, it can be done, but it's kind of messy. Plus, my answers are very hard to do as a reply by email. So unless it's something really easy, like, hey, I did question 4 and I keep on getting this, but the answer says I'm wrong. You know, what's up? And then I could probably fix. But most of the time, you probably need to do Zoom meetings, you know, because I can write on paper and you can hear what I'm saying. And let's move backwards.
I had a quick question about the homework.
Sure.
So as we're doing our homework, is it kind of like once we submit the answer for each problem, is that it? Or do we get a chance to redo it again?
You do. What you get is it should be set up for 3 shots. If you do it right, it'll do, is it a green tick or something? I think it's a green check mark. Yay, you're great. And then you move on. If you get it wrong, you get a second, then you get a third, and that's it.
Okay.
Right. So if I return now back to where I kind of left off, how do you draw 3D surfaces? Because they're a real pain in the butt if you had to do them, right? If you wanted to visualize it. So I have 2 programs here, one called GeoBra and the other one's called CalcPlot. I'm going to hit that one. Has GeoBra appeared on, it's appeared on mine, but has it appeared on your screen? Right. So you go up here and you type in Z equals X squared plus Y squared. And can you see the guy I talked about that looks like a monk's hat pointing upwards? And you can do some cool things. The green is the X, right? And rotate it. There we go. You see, you can orientate it. Actually, from above, doesn't that look like a circle? If I come on, there we go. There we go. And you're cool. Now, if you just change it a little bit, I don't know what I'm going to do. Let's stick a 2 here. And let's stay 5 here. Do you notice it's now an ellipse from above? But it's still got the kind of cup shape to it. Now, if you take this guy and one last play about, and you stick a negative there, do you think that's going to change the shape a little or a lot? You think? A lot. Okay. Whoa, a lot. The color scheme is not very easy to see. I don't know if I can change it to any other color. Not easily. Okay. Can you see the curvature going this way and this way? Do you notice it's also got a curvature going that way? It's a very weird kind of shape, that. So if you had, for whatever reason, a need to see what your multi-dimensional, your 3-dimensional, I should say in this case, function looks like, it's a surface, you could plug it into here and have a look. Now, that's the kind of thing, I kind of like these things, so that's the kind of thing you could play about with. And it's kind of cool. Any questions? We cool? Right, let's return back to our intro. So, Calc 4 is basically finding derivatives and integrals of multidimensional functions and then finding uses, you know, what can I do with it once we've done that? So let's get right into it and do an overlap. Suppose I had z equals x cubed plus y squared. If I asked you to find its partial derivative, dz dx, right, the partial derivative. Now notice that the d is not a hard d, it's a kind of curvy d. And that's a notational thing, and it actually does have a significance. This is notation that you would use in partial derivative world. This notation here, right, isn't that what you would have used in Calc 1 world, right? So people can tell just by the way you're writing it that it's a partial derivative, right? It's a multi-dimensional function with more than just x and y in it, right? There's an x, y, and a z in this case. Now, the rules for finding partial derivatives are very similar to normal rules. Don't you just consider x the variable and every other letter, you treat it as if it's a number. We call them constants. So in this case, you differentiate x cubed, you would get 3x squared. And what would you get from y squared?
It would zero out, right?
It is 0 out. So that is the answer. Now, if you do a partial derivative of z with respect to y, you get 2y. Now, it's not a surprise that they are different. In fact, it's more likely that they're never going to be the same thing, right? Against now and again, by sheer fluke, they may be equal to each other. But would you agree that the partial derivative of a function with respect to x and the partial derivative of that function with respect to y are probably not going to end up being the same thing when you're finished? Now, if we move up, sometimes your function isn't called z equals, it's called f of x, y equals. And no biggie. But this time it's going to be x squared y plus y squared x. And notation, you could be asked to find the partial derivative of f with respect to x, or you might see f with a little x. Right? So hopefully you're familiar with both those notations for partial derivative, right? They mean exactly the same thing, right? So let's find out what it would be in this case. Right, ignore that for a minute. With respect to x, this guy, when you differentiate it, don't you get 2xy? It's a bit like 5x squared or 20x squared, right? The 5 or the 20, the y, it's still there. So you get 2xy. On this case, with respect to x, what do you get?
Just squared, right?
Yeah. Now, if you wanted to find this fella, it would be that one, right? Are we good so far? Yeah. Just taking our time and moving up the food chain. I don't know which one I'm doing, a Z again. Let's go back to that one. Right, that one's a little bit weirder. And in this case, I could ask you to find the partial derivative with respect to x, and I could write it like that, right? So there's the two notations. They both mean the same thing. Let's use that version. Now, this is a Calc one chain rule. Remember chain rule from Calc 1, a function of a function. Now, x is the variable, right? So to me, this is like the sine of 5x, right? The sine of 20x, right? The y cube's just like a number, like 5 or 20. So if you want to differentiate the sine of xy cubed, you get the cosine of xy cubed. Agreed? And since it's a chain rule, don't you then finish with the derivative of xy cubed? Now, with respect to x, isn't the derivative of xy cubed just y cubed?
Yes, I agree.
Now, this mess here looks worse than it really is. Isn't e to the y squared just a constant?
Yes.
So this is like 5e to the x. So when you differentiate it, because the derivative of e to the x is just e to the x, do you see that the derivative of this is actually itself? That makes sense. Right. Now, let me give you a few moments. Try that one. You have a shot at it and then I'll do it. Okay, everyone. Any volunteers for this fella?
I got 3xy squared cosine of xy to the cube.
Yep.
Plus 2y e to the x e to the y squared.
Hopefully you got the same, everyone. Right, let's take that one step at a time now. Chain rule, right? It's the sine of a function, right? A function of a function. Differentiate the sine gets you the xy cubed bit, right? Cosine of xy cubed. And isn't the derivative of xy cubed with respect to y 3 y squared with an x, right? 3xy squared. So that's where that piece came from. Now we focus on this side. That's basically a constant. So really what we're doing is differentiating e to the power of y squared. Chain rule again, right? E to the y squared times the derivative of y squared, which is 2y. Tag the 2y onto the start, and there's the whole piece. We go. Now, let's show you a product rule. So that was partial derivatives where we needed to do some chain rule stuff. And let's find the partial derivative with respect to x. Now, as far as x is concerned, there's an x here and there's an x here. So what that is telling me is that I've got two functions of x multiplied together. And because of that, doesn't it mean I'm going to have to use the product rule? If you hear a squeak at the background, my dog has brought in one of his toys because he figures out I've ignored him for too long and it's time for me to play. But I'm going to have to ignore him a little bit longer. Now, it depends on who you got and how you learnt product rule. So I'll show you my version, but if you've been taught a different way, that's fine. I call the first guy F, I call the second guy G, and the product rule is F dash G plus F of G dashed. Is that the version of the product rule that most of you have used? There are some
Yes.
UDVs around as well, technique that I have seen. In fact, I've seen a technique where these two switch places, which I don't know why, but evidently that happens in America. I just choose not to do it. If you differentiate this with respect to x, you'll get negative the sine of xy times the derivative of this with respect to x, and doesn't that get you a y? So you're looking at negative y sine of xy times, leave the second piece alone, add, leave the first piece alone, and now we've got that guy. With respect to x, what's that guy's partial derivative? E to the x plus y.
Wouldn't it just be e to the y?
E to the 1 plus.
Okay, let me take that guy and put him over here for a minute. If you think of this guy as e to the x times e to the y, isn't that just a different way of splitting that up? And if I look at it from that perspective, won't its derivative be that? In other words,
Same thing.
it's the same thing.
That's what I got.
Right. Suppose I called it e to the x plus 5. This is a trick you can use if you're not sure what a partial derivative is. Replace the y, whatever, you know, y cubed, whatever. Replace it with a 5 or any number you want. If I differentiated that, would you agree that the derivative of that is still that? Right. And if that was actually y, you see, I get that. And if this was y cubed, I'd get that. Do you see the effect of that plus y is really the same effect a plus 5 would give to a derivative, right? In some situations, doesn't it have almost no effect on the answer, right? It doesn't change the answer in any significant way. On the other hand, wouldn't that make a difference?
Yes.
Right, because you do that guy,
Yeah.
won't you also then have to do a chain rule?
Yeah.
And differentiating with respect to x would leave you with that guy. But that's the same thing that would have happened if it was 5x. You see? Right, so if you get a little bit caught up, because sometimes there's just too much going on in your brain and you're like juggling 5 balls in the air, and you're thinking, what's the derivative of one particular piece? I know, maybe take it to the side here and play about with it, but change the y or whatever the other guy is, the constant guy. Just change it into a number like 5. Figure out what you would have done if it had been that number, and then just transfer that knowledge into the question you're really trying to answer. Right? Does that help?
Yes.
Yeah. Now, this is what I call style points. If you've had me before, you know what I'm talking about. Style points is just trying to make the answer look nice. There's not an awful lot that you can do in many of these questions, but I can at least pull out a common factor. And if you can, you should, right? Now, that won't be the biggest issue that you're ever going to meet up with. And I think WebAssign, for the most part, is very generous about how you write the answer down. So in other words, if you just wrote that down, WebAssign will probably give you a check mark and say you're correct. But I think it's good math to know how to factor things and to make them pretty. And I know, now and again, it's pretty rare, but I can imagine situations where maybe you could combine some terms together and some things cancel out with some other things, right? A whole load of nice bits and pieces. You could reduce it a little bit so it makes it look nicer. So when you reduce things or simplify them, I just call that style points, right? So you do some style points on it, make it look pretty. Any questions so far? Are we good? So partial derivatives with powers, partial derivatives with chain rule, partial derivatives with product rule. There's only one guy left, isn't there, from the major rules? Partial derivatives using, any ideas what I'm going to use? Quotient rule, right? How do you do derivatives when there's fractions, right? So let's do one. You can tell you're going to use a quotient rule rather than any of the other rules when this function here is a fraction and that the top and bottom contain the variable that you're trying to differentiate with respect to. So in this case, I'm going to just do the x version, right? So you see how there's an x squared in the top and there's an x in the bottom. And before you start saying, hey, I can do some algebra on this and make the question dead easy. No, 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 that is not true. You can't cancel that and that because these are added. They are not factors. Right? So that is not correct. Don't do it. Can't do anything to that. Right? Now, oh, while I'm at it, I could do something with this one. Pretty rare, but you know, if you see it, it's great because it saves you a whole load of work. Any ideas what I could do specifically to the top line? How I could factor it?
X plus y times x minus y.
Now, in this case, aren't these things factors?
Yes.
And if you are factors, you are allowed to cancel a factor with the same factor. So these two can cancel out. And now the answer is x take away y. And wouldn't you agree that would be very easy to differentiate with respect to x or y? But not for this one. Now I'm going to call the top guy F. I'm going to call the bottom guy G. And we'll do a partial derivative with respect to x. And so that's going to be f dash g take away f of g dashed over g squared. Hopefully that's the version that you're used to. Right. Have you noticed that today we have used pretty much every rule from Calc 1, but adapted it to the new situation? Chain rule, quotient rule, product rule, power rule, e to the something, you know, every function you could ever think of from Calc 1 has came back today. So none of the things that you've learned from Calc 1 or Calc 2 are irrelevant, right? They're actually guys you're going to be using the knowledge from this point onwards. Okay. If you differentiate the top with respect to x, you just get 2x. Agreed? because plus y squared gets you plus nothing, times the untouched g, which is x add y, take away the untouched top guy, differentiated by x add y with respect to x, is it not just 1? So f dash g take away f times g dashed all over g squared. And I'm going to do some style points on this, because I think I might be able to make it look a little bit nicer. So I'm going to distribute this, and that gets me 2x squared plus 2xy. And I'm going to take this guy and this guy. And it looks like I'm going to have an x squared, a 2xy, take away a y squared, all over x plus y squared. Not a lot of tidying up, right? Not a lot of style points. Would you agree? It just looks a little bit prettier than that does. And that's the goal. Make it nicer. This looks like a good point for us to finish. Is there any questions before we call it a day? Have we learned some cool stuff today? Okay, 2 smells. Okay, I'm working on that. Okay, a thumbs up as well. Okay, I will see you all tomorrow. Tomorrow, what I'm going to be dealing with is some more complicated versions of partial derivatives and how to find partial derivatives when the function is written like that, not z equals, but z squared equals, or when it's written like that. Now, these are also multi-dimensional functions. And the difference in these cases is that they haven't really been separated into z equals. Now, I could algebraically create z equals here, but I'm not going to. We're going to show you that you can actually find the partial derivative of z with respect to x and z with respect to y in both these cases, because that's the only partial derivatives that we're going to be interested in. Z is called the dependent variable. So when we do partial derivatives, it's always dz with respect to one of the other 2 variables, right? Right. We don't go looking typically for dy by dz, right? Or dy by dx, which might seem natural, but we don't go looking for them. In the context of this world, we're interested in how does z, the height of the surface, vary with respect to the x direction or the y direction, because that's really all partial derivatives are doing, is they're taking a surface and taking a vertical slice through it at either x equals 1 or 2, some fixed number, or cutting it the other way, y equals 1 or 2. And when you take a surface and you vertically cut it, don't you just leave behind a 2D curve? And so what the partial derivative is doing, it's finding the slope of that 2-dimensional curve, right, at a given point, x, y. And in one direction, you're making x the variable, in the other, you're making y the variable. So that basically means I'm cutting parallel to the x, or I'm cutting it parallel to the y. And that's the geometric interpretation of that. So these are surfaces, and you can still cut them that way. It'll be fun. And your algebra skills are going to get better. Right? And that's it. I'm going to go, oh God, one last thing. I'm so forgetful. we have participation points, that is coming to class and taking part. And the way that I keep track of who is here is that you will now say hi by going to the chat screen, and I get a copy of the chat, and I can then use that as my attendance, right? So if you can all just say hi and then bye-bye, that's us. Right, I got 11 people made it. Cool.
Thanks, Professor.
You are welcome. If you have any other questions, since officer is actually directly after this, if you just want to wait behind for a few minutes, I can answer your, particular question, one-on-one, so the rest of the class can't hear us. Oh, and this entire thing will be saved on Canvas. So if you want to go back and say, what did he say again? I can't remember it. You can look at the video.